Hello everyone, today we'll be presenting the XLOW solution for real-time video encryption. Full encryption of real-time video is considered a challenge for the computer science world. Many papers state that this is computationally infeasible, and this is mainly because solutions like AES and DES are too computationally intensive, so they do not meet the real-time requirements. So what current state-of-the-art solutions do is that they do some partial encryption of the video so that it can be processed in real time. So some of them do something like just encryption of the motion vectors, but we can see that the encryption is not very good. We just see like a distorted version of the image. Other approaches proceed by extracting just the region of interest. For example, in this case, they want to hide the faces of the people inside the video. So what they do is that they just encrypt these regions. How are these regions extracted? Well, computer vision can do this task. They can extract the faces and encrypt just these small regions. But it still is not a full video encryption. In order to do real-time video encryption, there are two main approaches. The first approach is the naive approach, which consists in encrypting the whole video stream or the bit sequence using a block cipher. The greatest advantage of this approach is that it's considered the most secure approach because one can fully encrypt the real-time video using a trusted block cipher such as AES or DES. However, as we mentioned before, this is considered computationally infeasible, and also this will result in an unplayable video because we're messing with the bit stream. The second approach is a frame-by-frame approach, where we transform the pixels of each of the single frames of the video. The advantages of this approach is that we can do pixel manipulation. So for current solutions, this is the only feasible approach because since we can do pixel manipulation, we can do some sort of partial encryption. And this will result also in a playable video. However, this is considered less secure since the video is encrypted in a selectively way, whether it be a region of interest or motion vectors or any other selectivity approach. What is the XLOW solution for real-time video encryption? First, we will offer a block cipher that is fast enough to use the naive approach, which is considered the most secure approach. Also, we have a full real-time video encryption using the frame-by-frame approach that is as secure as the naive approach because we encrypt the whole frame. And third, we offer homomorphism on real-time video encryption using the frame-by-frame approach. During this presentation, we will explore these three solutions. The naive approach. So the naive approach proceeds by having two elements. We have the camera and the authenticated user. So the camera captures the video and produces a raw video stream or a bit sequence that is encrypted within the camera, and the encrypted video stream is transmitted. Note that in order to have a naive approach solution, the encryption algorithm has to be lightweight enough to be run on the camera. So when we have the encrypted video stream, then it is transmitted to the user. So the user receives the encrypted video stream or bit sequence. Then the user is able to decrypt and recover the raw video stream and finally get the real-time video. XLOWS addresses this problem by using the XLOWS block cipher, which is a block cipher we developed that is very secure and very fast. So bit blocks are transformed into multivectors. Multivectors are encrypted using the triple product within a finite field, and this produces the cipher. Then the encrypted multivectors or the ciphers are transformed back to binary blocks, so we can have our encrypted bit stream. Now we're gonna proceed to see a real-time video encryption demo using the naive approach. So here we have the setup. We have a camera on a Raspberry Pi. We have our router. So the Raspberry Pi is gonna capture the video, encrypt it, then send it through the router to my computer, and we're gonna show the video here. So just to give you an idea, gonna start the unencrypted video. So here we can see the unencrypted video. As you can see, there's it's in real time. So now we're gonna stop the unencrypted video. Gonna terminate the process, and as you can see here, we have my encryption keys and my decryption keys, which in this time they match. And also let's do this on HD resolution. So we have HD resolution, and I'm gonna do my encrypted transmission on HD. So as you can see, this is real-time HD video encryption using the naive approach. Again, we have here our Raspberry Pi, the router, and it's coming here to my computer. Now, let's just make a little test here. Let me just terminate the process, and I'm gonna tweak the decryption key just by 1 digit. I'm gonna put 2 here. Okay, and I'm gonna try to start my encrypted transmission. And as you can see here, we have an error, and this is not producing a valid video stream. And this is because the decryption key doesn't match the encryption key. So I'm gonna terminate the process, and I'm gonna put the right key again, and I'm gonna start my encrypted video transmission on HD resolution. And as you can see now, I can get the real-time HD video encrypted.
The frame-by-frame approach. In order to encrypt a video frame by frame, it is necessary to have a means to encrypt images. So we developed a way to encrypt images pixel by pixel. So when we have an image, what we actually have is a matrix of pixels. So the pixels are converted into multivectors. Then the multivectors are encrypted using the triple product within a finite field. And finally, the encrypted multivectors, which are the ciphers, are transferred back into pixels, and we have an encrypted image. Here we have an image, an example image, which has an entropy of 7.0115. And we have the histogram of this image, which is the pixel or color distribution of this image. When this image is encrypted with X logos encryption, the entropy of the encrypted image is 7.99723, which is really close to the perfect entropy, which is 8.0. We can also see that the histogram of the cipher image is close to uniform distribution, which is far away from the plain image histogram with the irregular distribution. Therefore, it is computationally infeasible to derive any information about the plain image from its corresponding cipher image without the key. We compared our entropy with other state-of-the-art image encryption algorithms, and we can see that our entropy of the same image is the best one. Note that some of these algorithms might not be even fast enough to be done on real time, and also other encryption methods such as AES and DES are too slow for real-time requirements. So right now we can proceed to see a demo of the frame-by-frame approach by Xlogos. So in this demo, we're gonna have an original video, which is gonna be in real time. This is gonna be the encrypted version. This video is gonna be encrypted in real time and decrypted in real time. All is gonna be happening simultaneously. So please compare the original video with the decrypted video, and you will see that it's instant. The encryption and decryption is happening at the very same moment. Homomorphism. Homomorphic encryption states that the operations done on the plaintext should match the operations done on the ciphertext. So if these two images are added, we get this result. This is on the plaintext world. But if these images are encrypted using the XLOS encryption, we get these images. And if we add them, we get this result. And if when this result is decrypted, we have a match for the operation done on the plaintext. So this is homomorphic encryption for images. Homomorphic encryption for images can have multiple applications. One of them is digital subtraction and geography, where we can have an X-ray and then the patient gets injected some contrast, so we get another image, and then we can generate the digital subtraction and get a enhanced image. Well, with XLOS encryption, this could be done only with encrypted images. So we can encrypt these two images, subtract them, and this is the encrypted image result. When we decrypt this image, we can see that the decryption matches the enhanced image. Another application for homomorphic image encryption is surveillance. With image arithmetic, we can detect the difference between images or frames in a video. So let's say we have this frame and this frame, and we want to see what changed between these two frames. We just do a subtraction of these two images, and we can see that the pencil is gone. This can also be done on the encrypted domain. So we can encrypt this with XLOGOS. We can do a subtraction, and we can see that this is the difference. And finally, when we decrypt the encrypted result, we can see that the pencil is gone. Homomorphic image encryption can be applied for real-time video encryption if we use the frame-by-frame approach. The applications are multiple and can be very creative. For example, in this demo, we're gonna show a layer encryption. So on our camera, we're gonna be capturing a real-time video. Using computer vision, we can extract different regions or layers. This is the face layer, and this is the background layer. Then we can encrypt with different keys our layers. So we're gonna encrypt the faces layer with key 1, and we're gonna get this result. And then we can encrypt the background layer with key 2, and we're gonna get this result. Then, thanks to the homomorphism of our encryption, we can add these two encrypted results into a single encrypted video. And then this single encrypted video is the one that is transmitted. Then on the transmission side, we're going to be transmitting just one single video. And we can have multiple users that are going to be receiving this video. Let's say user A has key 1. So when user A decrypts with key 1, he will only get the faces layer. When user B decrypts with key 2, he's just gonna get the background layer or region. And if user C has both keys, then he is gonna get both layers, and he's gonna get the full video in real time. All of this in real time. Finally, we can see a demo of real-time video encryption using homomorphism. So in this demo, we're gonna have our original video, which is video in real time. With computer vision, we can extract the faces layer, and then we can have a background layer. Then we want to encrypt the faces layer with key 1 and the background layer with key 2. Then we're gonna add the two encrypted results into a single encrypted video. Finally, the single encrypted video is gonna be decrypted with key 1, and we're gonna see that we only get the faces layer. We're gonna decrypt with key 2. We're gonna get the background layer. We're gonna decrypt with both keys, and we're gonna have the two layers into a single video. All of this is gonna be happening in real time. So layers, encrypted layers, single encrypted layer, and then we can have the decrypted layers and all the video.